This is an analysis of the dictionary data structure by Philip Curl, Craig Wolfer, and Yu Wang. This video will touch point on the purpose of the dictionary data structure, the mechanics used in the dictionary data structure, and applications of the data structure. A dictionary is a mapping between two sets of items. It's often referred to as a dictionary because dictionaries link words to their definitions. Dictionaries are also referred to as maps, association lists, property lists, among other things. Before understanding a dictionary data set, you must first understand an associative array. An associative array is an abstract data type composed of a collection of key and value pairs, such that each possible key appears at most once in the collection. Some common operations of associative arrays include addition of pairs, removal of pairs, modification of values of existing pairs, and a lookup of a value associated with a particular key. The problem at hand in dictionaries refers to the task of designing a data structure that implements all of these aspects of an associative array. Some possible solutions for the dictionary data structure are below. The standard solution is the hash table. Another common and easily implemented solution is the binary search tree. Some other possible solutions include red-black trees, directly addressed arrays, AVL trees, and skip lists. Why do we need dictionary data sets? They allow users to very quickly look up and store information. They're also extremely convenient in comparison to many other data structures. The ability to link a key to a piece of information provides many valuable benefits, and these will be discussed in further detail later on in the movie.
So a dictionary data structure. Essentially, it works a lot like a traditional dictionary. All of your information, or your elements, are associated with a key, and then you can use this key to add, delete, and find members. Essentially, every key has to be unique. They have this innate set quality to them that for every key there's one element and you can't have multiple keys. So it's best when every unique element will have one unique key. Also keep in mind, these keys must be comparable. This is important for many implementations because ordered data structures tend to be able to access, add, and delete elements a lot faster. So it's very important when considering setting up your dictionary what you choose for your key. Now you may wonder, how can one implement a dictionary? Well, keep in mind these three main methods, the add, find, and delete. One very basic implementation is through an array. Essentially, you would store the keys in the different array slots. You would add new keys to the very end, and you could literally search to find and delete members. However, this is not really efficient, because you're going to have an average case of n for just about every operation, since you have to linearly search the whole thing. It really doesn't make use of the key's comparable nature, so it's only natural that this is not a very good implementation. A much better implementation is the binary search tree. Essentially, the nodes are the keys, and then you can navigate through the tree to both add, find, and delete, and the regular tree way. And as long as your tree is about balanced, the add, find, delete will be log of n methods on average. This makes it a much better choice. And now you may also want to consider implementing other methods, such as isEmpty and size, to meet your needs. And you can also implement a dictionary through other data structures. Essentially, any ordered data structure can work for implementing a tree. You just need to decide between them and consider what data structure will best handle your dictionary problem. Speaking of which, another problem you can run into is how do you load all your information. This is a serious consideration for larger dictionaries, because hard-coding elements is not possible when you have upwards of thousands of entries into your dictionary. One possibility is to read information from a file. This is often a very convenient option because information is often stored in text files, and this is usually easy to do. However, when you stop your program, you're going to have a load time every time, and this may or may not be an issue. Another option is to create a program generator. Essentially, a program generator creates the code with the information already there. So this is really good for distributing code, as it takes load time away from the end user. However, coding for this can be really complex depending on your implementation. So when you want to use this load method for your program, you may want to consider different implementation choices for your dictionary. Essentially, the overall idea is to tailor your implementation and your load method to your problem. You can ask your key questions like, how big is my dictionary? Will my dictionary need to grow and shrink? Is load time an issue? Access speed an issue? Look at these and figure out what data structure implementation for your dictionary will be best and what load method will be best.
There are some instances where implementing a dictionary data structure would be very useful. One of the ways that the dictionary data structure can be used is in a program that has the functionality of being able to search for words from a list of words. Just the name of the data structure itself gives a way in which it can be implemented. A program that is required specifically to search for words, or a dictionary program, will require the implementation of a dictionary. Another use for the dictionary data structure is in a game in which looking up words is important. In a game like Scrabble, for example, a dictionary would be useful in looking up words that you are unsure of. This slide shows two examples of the implementation of a dictionary into a game like Scrabble. These are in Java. On the left is the array implementation, in which words are added to an array, and the isWord method checks to see if the word exists in this dictionary. This is not practical for larger lists, however, like a list with a couple thousand words, or a couple hundred even. The implementation on the right shows an implementation in which words are read from a text file and added to a vector. While this type of implementation has a rather slow starting time, it is more practical for a large list, which is more likely what a dictionary contains. The dictionary data structure can also be used in programs that require fast lookup time. For example, programs that keep track of library book loans can use a dictionary. Because in the case of a library book loan, one book can only be checked out by one person, but a single person may check out multiple books. Assigning keys to book names, ISBN, or any unique characteristic of a book, and a value to the patrons using a dictionary will allow for a lookup operation of a book to return the person who has loaned the book. A program trying to implement a phone book can also use a dictionary data structure. In this case, you would assign a key as the name of someone with a phone number, and the value would be the actual phone number. This way, when you look up the name of the person, you will be able to obtain his phone number. However, this would require either no repetitions in names, or it would require more detailed information in the key, so that each key is unique.
So in conclusion, a dictionary is a very convenient data structure that uses keys for easy lookup. It can be implemented by basically any ordered data structure, and is very useful in handling large amounts of information very well.